Good morning. Welcome to the PACE seminar. The presenter today is Dr. Fahad Shania from Murdoch University. He's a senior lecturer there. And before joining Murdoch, he was at Queensland University of Technology, working as a research fellow, and then joined Curtin. He was a lecturer there before joining Murdoch. He's published a large number of papers, and some of his conference papers and journal papers have won Best Paper Awards. He's also the recipient of Australia-China Exchange Young Scientist Award in 2016. And today he will speak to us about interconnected microgrids. So let's welcome Dr. Fahad Shania.
Thanks very much, Tyrone, for the nice presentation. And good morning, everyone. It's an honor to be here. And I'm going to bother you for the next an hour or so with the outcomes of the recent researches which we are these days working on the field of microgrids, and more specifically in the field of interconnected microgrids. I'll try to first start with the general concept of what the microgrids are, why they benefit us, what they bring to us as challenges, and then furthermore into the area of interconnected microgrids and what are the research questions that has to be answered in order to make them technically feasible and realizable in our systems. So, I mean, feel free just to interrupt me, ask questions whenever you want. So, first I'm going to start with what generally the accepted definition for microgrids is in our systems and its main differences with the other standalone systems which have been there for a long while in our power systems. Talking very briefly about its importance to Australia and a very brief review of the recent microgrid projects which have been initiated in Australia and more specifically in WA, especially in the last 2 years. Then as a very brief review of what research topics has been interested in the field of microgrids in the last almost 15, 16 years that topic, that name or phrase has been put forward by the researchers. And then this new area, research area, that is system of interconnected microgrids, which I'm going to say what it is, why it is important for us, where we can really use those things, and then followed by some examples and then some research questions which they have to be answered, and the technical challenges which we currently face about these systems. Now, in very simple words, by microgrids, we usually refer to a cluster of distributed energy resources and loads, which their main principal job is just to generate electricity locally and distribute it to the local customers there. One important difference between what we call these days microgrids with the standalone power systems, which we have had for the last over 50, 60 years all over the world and in different parts, especially at remote areas, mainly islands, small towns, which are far from the other places that they are not connected to the main grid, is that there is a big tendency in having as much possible as we can renewable energy generation in these systems. So those standalone power systems which has been there for a long time, they were mainly based on diesel or gas type generators. But in microgrid concept, we intend to have more what we call non-dispatchable energy sources like wind or photovoltaic, and especially energy storage things like batteries, flywheels, etc. Now, one important characteristic about these microgrids is that we expect these systems to work in both modes of grid connected and off grid. So we assume they have a flexibility to work in connected with the existing utility when that utility exists and when technical constraints are allowed. And then when anything happens in the system, if we want to have if there is any fault in the utility or if there is any maintenance there, so this network can be isolated from the utility and survive for some time. So when they are trying to design these systems, they consider the self-adequacy and reliability in these systems, specifically for the off-grid or what they call off-grid, islanded, or isolated modes. Now, but what our utilities can get benefit by these microgrids is that, first of all, because the idea is that we want to generate electricity at the closest place to the loads, so definitely there will be a huge amount of saving in the power losses, which was usually previously happening over long transmission lines. So that is going to be the very first direct benefit of having these systems. And of course, because we are going to have renewable energy-based systems or a large penetration of renewables, which is going to reduce the amount of the fossil fuels, especially gas and diesels. So it's expected that the emissions and the air pollution because of that electricity generation reduces. Now, the other important thing is about we want to reduce the cost of energy or the cost of generated electricity over a life length of the project. So this is an important thing because especially for remote areas where the utilities have those gas or diesel-based systems, they have to either have pipes for transferring gas or like through containers, they have to transfer fuel. And this difficulty in transportation and the cost of that are some very big burdens on the utilities, which increases the overall cost of electricity generation. So by these things, we can expect that that cost of electricity over the life length of the project will reduce. Of course, its initial investment cost is much higher because we do have like renewable energy sources there and batteries, which are these days very expensive. Now, the other benefit which they can bring to our utilities is upgrading the aging systems. So continuously throughout the decades of the operation of power systems and distribution systems, the utilities have to upgrade their existing systems because whether they become aged and their performance degrades, or we do have new customers that are coming and they need a higher energy consumption. So changing the existing systems into a microgrid system means a system which can stand alone, generate its electricity which is required by its load, instead of upgrading the system, upgrading that like transformers, conductors, etc. It has been shown that over a long period of time, it's going to be more effective and more efficient than the upgrade of system. And then building sustainable future. So with all these intentions in every field of science that we want to make our systems more sustainable. Now, application of renewable energies here in the structure of microgrids, it increases the interest of people and utilities to say that, well, we are going to build sustainable grids by changing a portion of our system into microgrid or by changing the existing systems, especially in remote towns, which is possible into microgrid systems. So these are some very good benefits that microgrids bring into our utilities. Now, if we want to look into the Australian case, well, Australia is a very good avenue for the installation of microgrids. The main reason is that because we have lots of small towns and communities and that are distributed in remote, regional, and very far areas, which, as you can see, currently we have only like 2 small grid connected systems, one in the east coast and one somewhere here in the southwest of WA. And all those small towns there are mainly working in standalone power type systems, which based on the current practice that the electricity there are generated by diesel or gas-based sources, very, very little penetration of renewable energies exists there. So each of these small towns, they do have a good possibility of having their electric systems changed into a microgrid, which we expect a high penetration of the renewables to exist in them. We do have lots of Aboriginal communities spread all over Australia. Some of them, they have like low population from a couple of hundred to a few thousand. Well, of course, from a very non-technical side, to improve the life quality, electricity is one of the key factors. It always brings health, education, all those other services to our life and improves the quality of life. So one of the very good, again, avenues of utilizing microgrid systems is wherever we have remote Aboriginal small towns and communities, which currently they don't have electricity, or it's very limited, especially in the type of some fossil fuel type things. They can be easily changed into microgrid systems. And the last thing is that we have so many mining camps around Australia. There are so many mining places. Of course, the mining industry, because of the utilities, they need high power. But each of these mining camps, there are usually some camps where the workers, engineers will live there. It's easy to assume that there are suddenly over hundreds to thousands of people living in those camps. And all those camps are just like residential type things, which they need normal electricity, which can be, again, easily generated through some renewable type sources. And of course, that excessive type can be supplied by the diesel generators or gas generators, which they have there, and they are running those heavy utility things. So from these three aspects, we can see that Australia has a very good avenue for having microgrids in future. And if we go through the news over the last 2 years, we can see that there has been lots of interesting and good news about installation and or initiation of microgrid projects in Australia, and more specifically in WA. So currently Horizon Power and Western Power, they have started a few microgrid pilot projects around the state, which is something very promising. And it is not too far from now just to expect that probably in the next 5 years, after these pilot projects come to a more mature level, we can see that the utilities are becoming more interested in changing the existing power systems in remote towns and areas into microgrid type projects. There are photovoltaic cells and wind turbine cells in the range of a few megawatts that are being installed and then combined with the existing diesel generators or gas generators in order to supply that local demand in those places. So from these aspects, it seems that we have already started and our industries are already interested in having these microgrid systems, which is something very, very positive. Now, let's consider that, of course, the speed of technology growth in the field of microgrids was not as fast as what we can see in IT and computers, because whatever they propose, probably in 2 years' time, we can see that they come into reality. In power engineering, it has taken, in the field of microgrids, probably about 15, 16 years, just that now we can see almost every country around the world, they do have some sort of pilot projects initiating on that. Now, if I want to summarize over the last 15, 16 years what researches have been carried out in the field of microgrids, the first group of researchers were about the structures of microgrids. Well, the initial assumption that we will have an AC system, it's an AC microgrid, because over the last 70, 80 years, always our electrical systems were in the form of AC systems. So it was much easier for people to understand how the system is going to be designed, how it's going to be operated. Then there was some discussions about DC microgrid things. We were saying that, well, majority of our renewable energy sources generate electricity in the form of DC, like photovoltaic cells, wind turbine, etc., batteries. And we do have some loads that they can consume power in DC format. Now, there is a possibility that we generate electricity in DC format, distributed DC, and consume DC, and only for some specific type of loads which consume AC, then we will have a converter there, which converts the DC voltage to the AC that load requires. And then there was a combination of them, that was AC-DC systems, which we will have some generations which then generate DC, they are coupled to a DC bus, some generations and loads which are from AC nature, they are coupled to an AC bus. And then there is a power electronic-based converter between these two systems in order to allow the two buses to exchange power with each other. So again, how these systems are going to operate and the technical dynamic operation of these systems, each of these systems were one great interest of research among the people. The second one was about the type of the energy sources that we are using. Well, initially, we were always using the rotary type sources, like synchronous generators or induction generator type things. They did have this main characteristic common between them, that they did have inertia. Now, when we came to the renewable energy sources, which we connect them to the system through a converter, then we are losing that inertia thing, which is common with the other existing sources. So we might end up with systems which are pure inertial or rotary based. We might end up with systems which are a combination of rotary systems and converter interface. And with those advancements in research, now we have come to a point that we can run a purely converter interface system easily. So we can assume that all the systems are converter interface. But again, there has been some technical challenges how to operate this system. Some people, what they are doing is they are trying to say that we can control our converters to represent the very similar characteristic of what the rotary machines are doing. And that is, they are trying to virtually generate an inertia type performance there, so that it mimics those previous systems, and then understanding and controlling the system becomes very similar as what we used to do before. The other important things about power sharing among sources. Once you have a microgrid system, which is, as I said, cluster of different energy resources, the important thing is that how much power each of these sources is going to generate. Well, we can say eventually they are going to share the load, but we can say they share the load based on their rating. So the one source that has a higher capacity, it will generate a larger portion of the load. The one that has smaller capacity, a smaller portion. But of course, it's not going to be, might not be too much economical. So then there is a second option that what if we do some sort of like the economical dispatch thing which we were doing in the traditional power systems here, and try to control the amount of the power that each source is giving. Well, it is easy when we are talking about inertial sources, because they are totally dispatchable and we can control them. But when it comes about renewable energy based sources, they do have an intermittency, which necessarily it's not possible that we tell a renewable source to generate a specific power at a specific time, because probably because of the ambient conditions, that source is not capable of doing that. So there are those small problems when it comes to really handling this system from economical point of view. Now, the other important category of researchers in the field of microgrids has been about generally the control techniques of these systems. The whole idea initially started with the decentralized control, in which we were saying that if we have like a group of sources, we assume each one of them is going to work on its own, totally independent from the others, without a communication. It has a very good advantage, means that it's very cheap. There needs to be no communication infrastructure between them. But the problem is that you can't control the system overally. You can't make the system to behave in a certain way. For example, when we want to do about economics, we have to tell this system to generate this much at this specific time, and another like ratio, another power, another time. So we can see that we can't easily do that if we don't have that communication system, and they are purely decentralized. Then, with looking into that difficulties, the idea of centralized controls came up. And in that one, we mean that there is a central controller in the system, which that one governs everything, all the sources, how much each source should generate, and how much, what must be the voltage and frequency in the system at every instance of time, depending on the demand in the system. But of course, it's a communication-based system. Then we said, well, we can probably make the system controller a bit more complicated. We end up with a hierarchical control system, which we divide the whole control into different levels. We do have primary control levels, which each source does have its primary control, and in its capacity that we define for that, it will do a portion of the jobs. Then we will have a higher level control, which is called the secondary control, or the microgrid central controller. And what this system does, it tries to just coordinate those primary controllers of the microgrids. So it doesn't interfere too much with them, but it probably just gives some settings and set points for them to operate. And then there can be a third level of control, which is a distribution network tertiary controller, so that if you have a system composed of multiple microgrids, then that is going to coordinate those central controllers of the microgrids with each other. So probably we can say that this one is going to do much larger or higher level control system. This one is a middle level control system, and this is a very primary control level system there. And that is how it's going to be done. But the main difficulty of this control system is that there needs to be a very strong communication system, that every element in the system is almost going to communicate with each other, and they are going to transfer data. Well, usually as we said, the main idea is that we first try to go for remote areas and these things. In those cases, we want to do with the cheapest possibility, and we want to reduce the costs. That was the main intention. We went towards microgrids because we said that overall, over the life length of the project, it reduces the cost of energy. But adding those communications, again, makes the systems more expensive. So then the idea of this distributed control systems came, and that is what it says. It's a communication-based system, but with less communication complexity than the previous one. And that, in simple words, what it means is that one source does a specific action, gives some specific information to another source. That one, based on that received information and based on local measurements, it does something and then passes its output to the other one, and it continues among all the sources. So there is a sort of a loop of communication between them, but each source necessarily doesn't communicate with everything. So there isn't a central controller that tries to coordinate everything. Over a few samples of time, the whole system will come to that settling point. So it does have some advantages, especially from the telecommunication point of view. It's not a very strongly based on telecommunication. So if the communication system fails, we don't lose the system control overall. But it does have some disadvantages and some complexities in the case of which information has to be processed and which information has to be passed to the others. We want to minimize the amount of information that is passed. We want to have each of them to sort of become able to operate individually. Now, one thing which also is of general nature, and probably it's valid for both traditional power systems and microgrids, is the optimization of the system in two stages of planning and operation. So, of course, there has been similar to traditional power systems, there has been so much research in the field of planning of the system. So if we are trying to plan a system, in simple words, what is the most economical or the cost-effective combination of different renewable sources for that specific demand of that area, assuming that that is the profile of that area, assuming that these are the information about ambient conditions from which we can calculate what is the expected generation from solar systems, from wind turbines, and these things, and how we can minimize the overall cost of the system. And the other optimization is about the operationals of the system, so that if we are going to run the system, usually, let's say we do a day-ahead programming, and then within that day-ahead programming, we divide it into shorter intervals. We do, like, let's say 1 hour planning of short-term plannings, etc. How each of these systems should turn off, should turn on if they are dispatchable, and depending on the forecasting of the loads and the forecasted information about renewable systems, how we can operate the system in the best way. So, but as I said, that's more common between every traditional power system and microgrids. So these are the main categories of the research in the field of microgrids that has been done so far. So the new research area, which is here we can say, is with referring to this. Traditionally, I mean, tradition is in the last 15 years, we were assuming that the microgrid is going to either work in grid-connected mode or it's going to work in islanded mode. Of course, we assume that there's a possibility that it changes from one mode to another. And of course, it's possible that we have a microgrid which it does have that capability, but it always runs in one of those modes or in the other. Now, there is a third possibility, and that is, if we are talking about remote areas, let's assume we have a remote area, which for any reason we have decided, and we've come to this point, that the best way of supplying this town is having a microgrid system there. And then we have a competitive energy market, and then we have different companies which are competing to be part of that microgrid system. They want to invest there. They want to have their own renewable energy sources there and their own systems. They supply their own local load and gain benefit. Now, if we have a slightly large remote town, we might end up with having multiple microgrid systems in that town, each of them invested by a different company, each of them being operated by a different operator, and all of them independently and isolatedly working. Now, of course, each of them, when they want to design the system, they consider those reliability aspects. The self-adequacy of the system means that the system must be reliable on its own. It must be self-adequate means that the generations that we consider there must be capable of supply its load almost all the time. But of course, there are always some unexpected things which can happen in our systems, and that is the faults can happen in our systems, or with all those predictions, we may end up with like an instant in time that our load becomes very huge, that our existing generations with that conditions at that time cannot supply that load. So we end up with an overloaded system. Or we might end up with like a time instance that our load is whatever at a minimal value, and suddenly our renewable energies, the ambient conditions cause it that it can generate more power. Now, in each of these cases, the system operator has to either disconnect some of the loads, disconnect some of the generators in order to maintain the system stability. Right? Otherwise, there will be a whole blackout in the system because the voltage and frequency will deviate that much that the protective relays will disconnect almost everything, and it will continue sequentially until everything is turned off. Now, there is a possibility, so if we do have, let's say, a remote town with some microgrids, for example, let's say we have a large remote town, there is a river, so north of the river, somebody invests there and builds a microgrid there. In the south of the river, another company invests and builds a microgrid there. We might have this possibility that whenever one of these microgrids gets overloaded, or it experiences overgeneration from renewables, or there is a fault somewhere in the system that it has to disconnect some of its generators, it couples with one of those existing nearby microgrids and tries to exchange power with that, just to survive for that temporary period of time until either that fault is gone, or either that overloading has been improved, or if that excessive generation from the renewables drop. Now, so this idea is that we, instead of having a microgrid system which is always grid connected or always islanded, we end up with systems, with islanded systems which sometimes temporarily interconnect with each other to exchange power with each other and support each other. And the whole idea is that we don't want to consider it as part of the planning of the system, so we don't want to reduce some of the design characteristics, such as generation capacities or etc., assuming that always that source is there and it's going to help us. We want to say if those scenarios come up, there is a possibility that those microgrids provisionally interconnect with each other and support each other, and as soon as that necessity is gone, they become isolated from each other. So that is what we easily call the systems of coupled microgrids or interconnected microgrids or microgrid clusters. So we do have eventually at least 2 or more microgrids which they are sometimes going to connect with each other and exchange power and support each other. Now, again, so the main application of these systems, they are very good if we are talking about large remote towns. So we don't have a utility feeder there. If there was a utility feeder, they could have easily exchanged power, connected to the net, to the utility feeder and exchange power with that. There is no utility feeder, which is more probable in case of remote towns. And then there should be more than one microgrid system. Now, the idea is that they do have different operators, they do have different owners. Because if there is a single owner which owns both of the microgrids, they can be always interconnected to each other. It doesn't make a difference. But the interesting thing is that once we have different owners, each of them, they want their systems to be always islanded and isolated from each other, independent from each other, and only under emergency conditions they want to support each other. Now, what are the benefits of that? Well, first of all, whenever the system is overloaded, the first idea is that it has to, if there is energy storages there, let the energy storages give some power. If they are not available or they are empty, then it has to go for load shedding. Otherwise, the voltage and frequency will come below a limit, and it will eventually go towards instability, or we will see a non-standard voltage drop and frequency drop in the system. So to improve those things, the systems always do load shedding. So if we do have that technique, our load shedding is going to be reduced. The other thing is about excessive generation from renewable sources. Now, the question might be that what is wrong if we have excessive generation from a renewable source that our load can't consume? Let's curtail that excessive generation. The answer can be that, well, that utility, that owner of the microgrid has already invested money and built those things there, so it will gain more benefit if they continue generating power. So by interconnecting this microgrid to another microgrid, it can start selling that excessive power, which it doesn't need at that time, to the neighbor, and continue gaining that benefit. Of course, there can be a discussion about at what cost it's going to do that. Probably it has to do at a lower cost so that the other microgrid owner becomes even attractive to buy that. Even if he doesn't need it, he can store it in its batteries and later consume it. So it's going to eventually be beneficial for him. And then in case of faults, having that possibility of coupling microgrids, it's going to improve the self-healing of the system, the reliability of the system, and its resiliency. So these are the other benefits that our systems can get if they do have that possibility of temporary interconnection with another microgrid. So if I just want to show an example, let's say, well, this is in the concept of a large distribution network. So we assume that we have different couple of microgrids in the system, and then we can cluster those microgrids. That clustering can be because of geographical zone or anything like that, or because of the agreements of the systems, or because of what technically is more meaningful for their interconnection. So we say, let's say if for one of these systems, it gets some overloaded, what we can have is that with the proper closing of the switches between them, one or multiple of these neighbors can supply that one, and it's going to exchange power. Because of that clustering, we can say that, well, if there is a problem in any of these microgrids, only one of these three or combination of them are going to happen, and none of the others are going to contribute. Or we can allow that. It depends mainly on the technical constraints, depending on the line impedances there, so that if they connect, how much will be the power loss? Is it meaningful to transfer, let's say, 100 kilowatt from 10 kilometers other way, or it's more meaningful if it's transferred from a distance of, let's say, a couple of 100 meters. So all those considerations can be there. Now, to achieve these type of systems, we have to answer some technical questions. And these are the challenges that have to be addressed in order to make those systems feasible. The first one is that, what is the conditions or criteria based on which we can understand one microgrid is in need to be coupled with another neighboring microgrid? So for example, if it's the overloading of the system or overgeneration in the system, or if there's a fault, definitely there should be some criteria defined for the system so that these actions should be done, should be detected, these conditions to be detected as soon as possible. Now, one of the easiest ways, there can be different ways. Now, I'll go through in the next, first I'll go through all the questions, then in the next couple of slides, I'm coming back to each of them and discussing them a bit more. The second question is that, now we notice that one microgrid has some need for that interconnection. Among the other existing neighboring microgrids, which one of them we should choose? There should be a criteria in order to choosing the best microgrid from the other existing microgrids. Now, the third option is that what must be this is a more planning stage discussion or question. What must be the suitable structure and topology of interconnecting these microgrids? So let's assume one utility makes this microgrid for itself, another company comes and makes another microgrid for itself, and then there are three of them in the neighborhood. How should they be coupled to each other? How should be the physical links between them? Then let's assume we found out that one microgrid needs problem. We have another microgrid, let's call it a healthy microgrid, which wants to couple with that and connect with that. Well, how should they synchronize with each other? Well, that's very easy if we are talking about two microgrids, but once we are talking about 2 or 3 microgrids with each other, depending on conditions, that synchronization might be difficult, and there should be a specific strategy how to do that. The next one is that, of course, we shouldn't allow any interconnection which will result in that healthy microgrid to become unstable itself. So I have a healthy microgrid which is stable. I want to connect it to another microgrid to support it, but the combination should be a stable system. definitely. So we shouldn't allow any interconnection that will lead to an unstable system. But then what is the criteria to define it before really doing that? And the next one is that, as I said, that whole thing is a provisional or temporary connection. When or based on what criteria are we going to detect that that necessity has now been removed and they can be isolated to the previous case, like to multiple independent and isolated microgrids? And the next one is that once I do have that system of interconnected, how is the system going to operate? What is the role of each source there? What is the role of the primary controllers, secondary controllers, tertiary controllers? Are they going to fight against each other? Or how are they going to collaborate with each other? So again, that is some dynamic operation questions that has to be addressed there. Now, I'll go through each of them very quickly. Defining those criteria for understanding that there is a necessity for interconnection. Well, in simple words, we can do it in two ways. One, we assume that we have a centralized approach. It means that there is a central controller which sits somewhere, probably in the highest control level, which is the tertiary controller, which monitors all the microgrids. It is going to receive information from all the microgrids, and based on that information, which is usually can be the actual active power which the sources are generated, and it has in its mind that what is the total capacity of these things. So it can easily know that whether it is generating up to its limit, so it means that it's almost very close to overloading of the system and these type of things. And of course, we can have a decentralized way, which is much easier. But then the question is that how we should do that. The easiest way is that we try to monitor the frequency in each of these systems. And then, because frequency always shows a good relationship between the generation and demand imbalance between the system. So as we have more demand in the system, or the demand tries to be more close to the boundaries of the generation capacity, we can see that the frequency comes down below and below. And once we can say when it comes below a specific limit, we define that that is very close to the overloading, and that is the time for interconnection. That is very easy if we have only a 2 microgrid system. So we have 2 microgrids which they want to couple with each other. But again, if there is a multiple system there, then that becomes more difficult, because if there are, like, let's say 4 microgrids, 2 of them simultaneously detect that the frequency is below a specific limit, then to each of those 2 healthy microgrids they should connect, because their overloading might be such that it makes the whole coupled system overloaded, which is something undesired. Now, for some of these work, we have done some preliminary studies which has been reported in some conferences and journals, but still there are lots of work to be done in these fields. Now, the second question is that once we notice that one microgrid needs support, how to select a suitable microgrid or a combination of suitable microgrids? The first one is a decision-making approach. Means that we try to make a selection out of some available or considered alternatives. Now, the trick here is that there can be different criteria to be considered, like the criteria, if I want to call them, the cost of energy offered by each microgrid. If I'm an overloaded microgrid and I want to connect to one of the existing ones, one of the things which I want to consider is that which one of them is offering electricity cheaper for me. Definitely, I will prefer to go with the cheaper one. The power loss, if one of them is very far, so definitely there will be a larger power loss. So I prefer to go with a closer one. Reliability, if I'm going to connect with another microgrid, I prefer to connect with one that has a better reliability, not with a worse one. And there are lots of these type of things. Or the maximum voltage and frequency deviation. If I'm going to eventually couple with one, I prefer eventually my combined system sees less voltage and frequency deviation. That's a privilege. So we do have a decision-making approach, which what it tries to do, it says if you have different criteria, and each of them they might have different weightings, depending on what those utilities want or what they prefer. So it tries to look into all those alternatives and select the best alternative among them. This is a very fast approach, very, very fast, but the problem is that it's not necessarily going to give the optimal results. We can use optimization-based techniques, But these optimization-based techniques, they can do lots of things there. They come more under the centralized approach, where you have the general information and almost every information in the system. But usually they are very slow. Now, considering the fact that we want this whole system of interconnected microgrid, let's say a system is overloaded. At the same time, our under voltage or under frequency relays picks it up, and then they want to operate after that initial setting time that has been designed for them. Let's say, for example, it's 1 minute or 2 minutes or so. Now, the whole idea is that this algorithm should notice and detect that there is this problem, should try to select the suitable ones, should give enough commands to them to synchronize and connect with each other, and this whole thing should be formed before that operation of the protective relays. Otherwise, the system, there has been some disconnections, either in the loads or generators, and there is no any more point if you want to couple them. So that's why that speed of operation is very, very important. About the planning stage, let's say we have like these 5 microgrids there. One important thing is that how much money do these operators of the microgrids, they want to invest in building those interlinking links between them. So one option is that, well, all of them, they connect to a center point there, probably the shortest distance for each of them. Now, another option is that let's assume there's a radial line or a loop line, and each of them, they are connected to that. Then there can be the most comprehensive one, that every microgrid has been connected to every individual microgrid, right? But probably this is going to be the most costly one, and nobody will go after that, especially in remote area type things. But the advantage of that one is that we can have multiple systems of coupled microgrids. So for example, let's say if this one is overloaded, and for any reason our strategy defines that this one is the best option to couple, we can close this link between them, and they become coupled to each other. And then after some time, after a few minutes, if this one also gets overloaded, our system can say, well, now it's best that this one couples with that. So we end up with one system of coupled microgrid here and one system of coupled microgrid there, multiple simultaneously in the system. But that is not possible in either of them. Because let's say if this one is overloaded and the system connects to this one, so this link is connected, if anything else happens, that thing has to be connected to their combination. There is no other way for them to go ahead. And then we might end up with some connection which a microgrid is connected to one, and then another microgrid to 2 or 3 or more. So to answer that question, we definitely need to do a planning stage activity that it has to consider a couple of things. First, how much money they want to invest in building these links. The second one, how often this system is really going to be used. If it's going to be used, let's say, 5 times per year, then probably you have to go with the cheapest option. But if it's going to be used 5 times or 50 times per day, then there is more meaning for that to have more investment there. And of course, this cost must be much smaller than the cost that each of those utilities are putting in order to improving the design of their own internal elements, like batteries and energy storages and dispatchable sources like generators. Because if they are going to spend more money on some interlinking links, they can put less in their internal things and improve their system's self-adequacy. Then there is no need for all these things there. And then the other thing is that whether we want to have only one system of coupled microgrid or multiple of them simultaneously. So each of these things will affect this parameter. And of course, when we come about the structure, another important thing is that let's say we have a couple of microgrids which they are connected to through a line, like through that the previous one, figure B there. Now, let's call it the power exchange highway. Now, what must be the characteristic of that link itself? Is it going to be a 3-phase, 3-wire system? Is it going to be a DC voltage link? Is it going to be a single-phase line system? Right? Because we eventually want a power transfer capability between the systems. And then depending on what type of switch or power electronic converter we use there, we can have different options. If it's going to be a 3-phase system, well, that's easy. We can have some just like switches there, and whenever they connect, the whole thing is done. But if we want to end up with a DC system, then we need here a rectifier inverter type system, a bidirectional type system, which converts AC to DC and DC to AC so that it provides bidirectional power flow. And we might end up with a single phase system, and then we must have like a 3-phase converter to a DC and then a DC to a single phase AC inverter there. Now, again, if we have each of them, how are they going to operate under two schemes of central control and decentral control? The most critical ones is the decentralized control, because if you have this converter there and this converter, how is it going to notice that this one has power deficiency and this one has power excessive, and then it is going to push the power in this direction and this one is going to absorb and give it there. So that decentralized dynamic control of them is a very important thing. And again, so that power electronic based converter thing that we use as the switching device there, what is its structure is, and how it's going to be controlled. Now, about synchronization, I just start with this example. Let's assume we have a microgrid that has been overloaded. We have another microgrid that we found that it's healthy and it wants to be connected to that. Well, that's easy. What we can do, we can tell the switch to immediately close. And then we tell the switch of this one that wait and synchronize with this system. And once you're synchronized with that, you just close it. So it can be done under two ways, a forced synchronization or a natural or like an unforced synchronization. In the unforced synchronization, what they do, because they do have two different frequencies, so if you look at the vector, it's just like that. One of them is rotating, the other one is rotating with a different speed because their frequencies are different. And once they come and stay over each other, that's the time that they can close easily. But it might take a long time, depending on how the difference between frequency between these two are. And then we need definitely a communication system between them that what detects what action it gives to what. So for example, that control switch, that switch which we have there, it has to get this synchronization command from its central controller of the microgrid. And then that command to the central control of the microgrid, it has to come from the tertiary controller which controls all those things. So there should be a communication link between them, and they shouldn't overlap with each other's internal functions. Now, that stability thing, there are two important stability perspectives. One of them is a small signal stability of the system, and that is if you have one system which connects to another system, eventually we have to look at the system of coupled microgrids, and we must be sure that that system is stable. Usually we talk about the frequency and voltage deviations in the system, that they are within the acceptable range. Now, the second part is the transient analysis stability, and that is I just detect now that this microgrid needs the interconnection. I find a suitable one. I give a command for them to synchronize. I must be sure that before that synchronization is achieved, this system is not made unstable itself. So it depends on the rate of the drop of the voltage and frequency, so that if that rate of drop is very, very fast, and then that interconnection will take a long time. So that system has been already reached to the instability point. So then, and that condition, intercoupling of them is not a good option. I should immediately go for tripping the sources there. And those isolation of microgrids, under which conditions we should detect them, well, how should we detect that that interconnection necessity has been removed? Again, probably frequency can be a good option. If we can see that the frequency in the system of coupled microgrid has gone above a limit, that limit has to be defined. And because everything in the system, there is some uncertainty and intermittency there, we shouldn't go after defining a specific number, let's say like 50.3, let's say, or 50.2. We have to define it based on, for example, the power flow in the switch that we can see. We say, well, if there is a link there, if I'm just monitoring the power there, if that power flow over the link becomes below a limit, it means that, well, then this microgrid doesn't need excessive power, doesn't need the support of this microgrid, that it can be disconnected. So a combination of frequency, the power that is flowing through the lines, and these things can be considered there. And how should we notice that if there is a fault happening in the system? So if I have a system of coupled microgrids, of course those systems should be immediately isolated if there is suddenly an unexpected fault happening in one of them. Because we want, it was good that they support each other, but if there is a fault in one of them, we want this microgrid to be isolated immediately from that one so that those fault impacts are not affecting the other microgrid. So those type of things. And then dynamic operations. one important thing is that what is going to be the functionality of the secondary controllers of the microgrids and the tertiary controller after they are coupled with each other. Because as we said before, each central controller of the microgrid wants to define the set points for its primary controllers. Now, that is one central controller for the microgrid. If we have two microgrids like that, but they are coupled with each other, we can't have two central controllers, because then this one might change the set points of this in a specific way, which that one doesn't want to do that. So they will continuously start fighting. This one will reduce something, that one will increase, that one will further play with that. So there should be settings, how these things, which element, which control system is going to be responsible for what. And what about the communication link failure? If we have suddenly a system of coupled microgrid, and then there is, which is everything is based on communication here, of course very limited, but still there is communication. If there is a failure in the communication system, how should we recognize that those two microgrids should be isolated or stay in touch? So there should be a backup of operation looking into those type of things, so that if the flow of information from the communication link is broken, then what are the strategies that we have to look for and try to locally understand the situation of the system. And the very last important thing is the power trade among those microgrids. So how those two microgrids are going to exchange power with each other. So and all those concepts of power market can be discussed here. Are they going to bid for each other? So let's say one microgrid is saying, I am the problem one. I want some excessive power. There are two or three ones. Are they going to give the same amount of power? I mean, are they going to give the same cost of energy, or are they going to compete with each other in order to offering a better price such that it attracts that one to connect with that? But of course, it must be some meaningful costs for that, so that they also get benefit. So that power trade between them is also another concept. Or another idea is that we have to minimize the power trade. So we have to run the systems in such a way that there is a minimal power traded between them. That is also another aspect there. So these are some of those dynamical operation questions which have to be answered. And sorry, I was speaking too fast, trying to cover everything there. Sorry, I skipped a few points. I'm more than happy to answer any questions.
All right.
Thank you.
And see, most of these microgrids will be powered by renewable sources, Fahad. So what is your opinion, like how critical is it to be able to actually predict the amount of energy that these renewable sources can generate? Like how important is short-term prediction in these microgrids?
It is very important. I mean, I know that these days there are lots of studies going on about predicting two things: the load demand consumption and the generation. And from generation, mostly what is important is about renewable systems and photovoltaic systems. For these systems, we can do very long-term planning. Usually, if we can do probably in the range of 5 to 10 minutes planning, I think that's very ideal. For example, if for about photovoltaic systems, I know that these days there is a technology called sky cameras, which what they do, if there's a large photovoltaic system somewhere, they try to put at 2 or 3 points around that some cameras which they are looking only to the sky, and they are just monitoring the movements of the clouds. Based on image processing, they try to do that analysis of the figures. They find that how thick the cloud is and what is the speed of the movement of the cloud. And then based on those things, they try to predict that over the next 2 minutes or over the next 10 minutes, because this huge size of cloud is going to cover our photovoltaic system. So it's expected that its generation, for example, to reduce by 10%, by 20%, by 30% this way. So it is very, very important. And the more information we have in that one, the system can train itself and be ready in hand. And it won't be this way that something happens, and then because of voltage or frequency deviation, we notice there's a problem.
Just have one final question to you.
Sure.
You were talking about isolating microgrids after it's been coupled. Yeah. And one of the things that you're looking at is actually the frequency deviations. And if for the coupled system, if the frequency goes up, that means there is sufficient electricity generation, hence the frequency going up. But that alone, obviously, I think you stated, is not sufficient to actually decouple the system, because one of the microgrids could be generating all that power,
Yeah.
and the other may not be, and
Absolutely.
the frequency can go up. So I'm just wondering how the frequency, that measurement can be important at all, because one of the microgrids can be generating everything,
Yeah.
and the frequency could be going up, and that's no indication to actually
From the other one, what's
to decouple, yeah, because you don't know.
Absolutely.
So how can obviously this give an indication whether to decouple the system?
Well, in the works that we had conducted so far, we were assuming two parameters. One of them was frequency, but not only that one. At the same time, we were looking about the amount of the power that is transferred through the line as well. So if that power, we used to say that if the frequency is above a limit and the power is below a limit, now again, both of them, they are not fixed values. They are as a function of the frequencies of the system, and depending on the available information which we have about the capacities of the generators there. Because from that, knowing the frequency and knowing the total capacities of the systems and knowing which source is working or turned off, we can roughly calculate how much each source is generating at that time. So, and then if we look at the power transfer between them, we can easily say that, well, that one is supporting the other one. Now, but still that power is not a very good criteria, because from power we can refer to active power or reactive power. We might have a system which it doesn't need active power, but it needs reactive power to operate. For example, it has a voltage drop problem, which for that we have to supply reactive power. So the second microgrid is actually supplying almost very minimal active power, but more reactive power. So again, when we come to the power, we shouldn't only consider active power. So we were considering both active and reactive power separately, and the frequency, and then a decision based on all these three parameters. As you said, it is very hard to judge based on only one of them.
All right, I think we've already gone past an extra 5 minutes, and let's thank Fahad once more for a very interesting presentation.
Thanks very much for having me here. It was an honor.
Thank you. Thank you.
Thank you.